All right. Good afternoon, everybody. Let's start our lecture today. Now, in our previous lecture, we have discussed about two-dimensional motion, right? But we discussed it. We discussed this motion in a so-called kinematic waves. We know how to describe the motion by using quantities such as displacement, velocity, and acceleration. And we also know the relationship between these three quantities by using differentiation. Now, but we haven't dealt with the real-world problem yet. We haven't dealt with force. We haven't dealt with the kinematics part of the problem. We haven't explained to you how the force is related to acceleration. Now, in beginning from this chapter, we are going to do that. We are going to introduce to you the origin of the change in the state of the motion. That is the force. And we also would like to introduce to you a way to solve the motion given some kind of force is acting on the body. And that involves solving differential equation. Now, we will only talk about the simplest differential equation in this course. But hopefully, through this example, through this simple example, I can give you an idea of how of what is the basic, the fundamental principle of mechanics. Now let's get started. So this chapter is called solving problems in kinematics. Now, what is a fundamental problem in mechanics? Now, in the beginning of this course, we assume that we have a description of motion given by the position of an object as a function of time. So we are given x as a function of time, and then we find the velocity and then accelerations of the object at different times by using differentiation, right? This is our first approach to the problem of kinematics. But in mechanics, when we are dealing with real-life problems, we are usually interested in the reverse problem. What is that reverse problem? Is that we want to know when a body is affected by forces, when the body is affected by something, okay, something push it and something pull it, how would the body move? That is our fundamental problem, and that is most of the mechanic problems are concerned with. And needless to say, we have the Newton's second law that governs the motion. So we somehow know the acceleration of the body if the net force acting on the body is given. Then the net force is related to the acceleration simply by Newton's second law. And Newton's second law, we will discuss it in detail in the next chapter. But let us assume that we know this in your high school study. And the acceleration of a body is simply the net force acting on the body divided by the mass m of the body. So the net force is proportional to the acceleration. Now, so if F is given, if I know what forces are acting on the object, I essentially know the acceleration, right? But my ultimate goal is not only knowing the acceleration, but I want to know the velocity and the displacement of the object at different time. So I have to go back. After knowing the acceleration from the force, I have to find the velocity and then the displacement. Now look at this schematic diagram. When we start our discussion in kinematics, we start with the position as a function of time, and then we have a differentiation of it, and then we arrive at the velocity. And then we differentiate the velocity once more, we arrive at the acceleration. Now, if we go in the reverse direction, we have the acceleration now, and we want to find the velocity and then the position of the object. So when we are going in the reverse direction, we expect an operation that is the reverse operation of differentiation. Okay, if I go from x to v, I need a differentiation. That means when I go to v to x, I need an inverse operation of the differentiation. And needless to say, I think you know in your high school study that the inverse operation to differentiation is integration, right? So by doing an integration from of A, I should get the velocity V. And by doing another integration of the V, I should get X. So that's how the problem proceeds. Now, but this is not that simple. The problem is not that simple. Why? Because in most of the problem, the acceleration is not given, or the force is not given explicitly as a function of time. If it's given explicitly as a function of time, then I can integrate it with respect to time to get the velocity and then the and then the position. But it's not given to be expressed as a function of time. Now I have the following example to illustrate why it is not given as a function of time. Now for the first example, I have a mass hanging on a spring. So you expect an oscillation vertically, right? So when I pull the mass downwards, it has a displacement, the spring gets stretched, and when I release my pulling force, then the force on the spring will oscillate the mass. So the mass will begin undergoing oscillation. Now, there are actually two forces acting on the mass. The first force is, of course, the force of gravity, which is acting downwards. It is a constant. But there's another force. It's a force from the spring. Now, a simple model for the force of the spring, which is not necessarily very accurate, but a simple model, is that the force acted by the spring, acted on the mass by the spring, is proportional to the extension of the spring. So if the spring gets stretched more, the restoring force is larger. Okay, so I have the force of the spring be proportional to the extension, which I denote the extension by X. And the proportional constant is K. K is called the force constant. It is a characteristic of the spring itself. And there's a minus sign to denote that the restoring force and the extension are in opposite direction. We pull it downwards, we pull the block downwards, and so the restoring force is pulling the block upwards. Okay. Now you can see here, the force on the spring is not given as a function of time. It is given as a function of position. Okay. If the mass here is in a different position, it experiences different forces due to the spring. If it pull it downwards more, then the restoring force of the spring will be larger. Okay, so F is a function of position. Another example is a baseball traveling in air. Okay, suppose a baseball now have a certain velocity v in air, and the force of gravity is always acting downwards. It's always a constant. But there's also a drag force. The drag force is due to the air resistance. When the ball is, for example, flying in this direction along the direction of the velocity, the drag force is in opposite direction because the air resistance always opposes the motion. Okay, so the drag force is opposite to the velocity, and a simple model of the drag force may be the drag force is proportional to the velocity. B is a proportional constant, and the minus sign means the direction of the force is opposite to the direction of motion. Okay. Now you can see from this model, I can see the force is again not given as a function of time. It is given as a function of velocity. Now, so this in the example on the left, the force is given as a function of X, while in the example on the right, the force is given as a function of the velocity. And in both of this example, the force is not given as a function of time. So without knowing the expressive form of the force as a function of time, you don't know how to do integration, right? Because you don't know X and you don't know V, you don't know how they depends on time. So that means you cannot do a straightforward integration to find X and V. So what will be happening? We all know that the acceleration of an object is a second derivative of the position with respect to time. If you know the X, the displacement of the object at different time, you do the second derivative, that is give you the acceleration. Now the force acting on the object is known, right? But so the acceleration is also known. But the acceleration is known, not an explicit function of time. It may involve time, but it may not be the only dependence. The acceleration may also depends on the position of the object. So I write the acceleration as a function of the position of the object, like for example, the example of the spring. And it may also be a function of the velocity of the object, like for example, the air resistance. So although this function of A is known, it is given as a function of perhaps the time t, and also maybe the function of position and velocity. Okay, and I know this function A because I know the force acting on the object and I know the mass of the object. Okay, so this is a given function, but you can see X and V are the unknown, right? We don't know X and V beforehand. This is our goal. We want to solve it, right? So we don't know what is X and what is V. Okay, and on the left-hand side, you can see X is also unknown. We don't know X. That is what we want to find. Now, so we come up with the unknown incorporated into the function of A. Okay, we don't know X, so we don't know dx dt, and again, we don't know d squared x dt squared. They are all unknown. Okay, but they couple in a very complicated way in such an equation. And this equation is known as a differential equation. Okay, this differential equation is sometimes known as the equation of motion, because if you are able to solve this equation of motion, then you will be able to describe the motion of the object. You will know the velocity and the position of the object at different time. Okay, so our fundamental goal is to set up this differential equation when the acceleration is known, a known function of tx and v, and then eventually we aim at solving x as a function of time. Okay, from this equation. Now this equation is actually in general very complicated, and so I'm not going to discuss a very difficult example with you. I only will discuss the simplest example with you, and that is a requirement of this course. We will not deal with the complicated example. Okay, now when you solve this equation, you have to impose the initial condition. Now, what are the initial conditions? The initial condition is the position and the velocity of the object when the motion starts. Now, when you are told to solve a motion, you should be given the initial position and the initial velocity, right? That is the initial condition that you have in order to fully describe the motion. Otherwise, without knowing where the ball is, without knowing with what velocity the ball is thrown, you have no way to know where it will be at a later time, right? So the initial conditions are important for you to fully specify the whole motion. Okay, so that's why during solving the differential equation, you also have to impose such known condition into the problem, okay, in order to arrive at the full solution of the problem. So a brief summary of Newtonian mechanics is the following. The fundamental problem of Newtonian mechanics involve the first thing, knowing the net force acting on a body, knowing which kind of force acting on a body, and we also can describe the net force by forming a vector sum of all the forces. And then these forces are given as a function of position and velocity, so that we will be able to express the net force or the acceleration in terms of the position and the velocity. Okay, and so we have a differential equation set up. Okay, and that is called the equation of motion. And by solving this equation of motion and imposing some initial condition, you will be able to find x and position and the velocity v as a function of time. Okay, so if you can do it, then you have already fully solved this problem. But before going further, because I talked about solving differential equation and I talked about integration, right? When you go from A to V to X, effectively you are doing an integration. but sometimes not in an explicit way. When you solve a differential equation, you actually integrate the equation. So it is time for us to have a brief review on integration before proceeding further. Okay, so in the next maybe half an hour, let me have a brief review of integration review before going further to solving differential equation. So let's have a stop here, and then we go to the chart mathematical notes of integration. Okay. Now let's review the definition and meaning of integration. Okay. Now you might have learned integration before in high school, but sometimes the teacher might not explain to you very clearly the meaning of the integration. In some teaching, integration may just be described as an inverse operation of differentiation, but integration has a meaning on itself. And in order to understand mechanics, you have to understand that meaning of integration very clearly. So let me take this opportunity to explain to you the meaning, the true meaning of integration. Now, if you talk about the integration, you have to go back to its basic definition, and that definition is the Riemann sum. Now, there's a term for this sum, and it's called Riemann sum. It is invented by the famous mathematician Riemann. Okay, Bernard Riemann. Now, what is that? Suppose I'm given a function of t. Okay, so I plot a graph of f versus t, and the back curve is the graph. Okay. Now I consider the area bounded below by the graph. Okay, and then I chop this area into many thin slices. Assume that each of the slices has a width delta t. Okay, so delta t is the width of each slide, and the height of the slide, for example, at the position ti, I can label all this slip by using 1, 2, 3, 4, by using number. The number 1, number 2, number 3, number 4, maybe up to number n. And on the I strip, the time is ti. Okay, so at this time, ti, the value of the function is f ti. So it represents the heights of the graph, right? The value of the function is the height of the graph at this point. Okay. Now, how about if I form a product between this f and delta t? If I multiply the two together, it will become the area of the strip. That is the orange area. Okay, that is the orange area. So I can do the same thing for the other strip, and I add up all this area. So I form a summation. This summation means now I sum up all the area of the strip, right? And then I will have an approximation of the area bounded below by the curve, right? Now you can see that this summation is actually not the area, because you can see this is a smooth curve. The function f against t is a smooth curve, while the summation consists of individual strips, which are rectangle. And in some places, the rectangle may be higher than the original graph. And in other places, the rectangle may be lower than the original graph. So the area of the rectangle may not represent the area bounded below by the curve along that strip, right? And so that would not be an accurate representation of the area below the curve. But imagine now, if I let delta t tends to 0, if I consider the area to be made up of a lot of those kind of strips, and the width of each of the strip now tends to 0, they are getting very close together. So the difference between the curve and the strip will become smaller and smaller until eventually when delta t exactly tends to 0, and we make up the area by using an infinite number of strips, the summation will tend to the total area under the curve. And we call that by an integration. That is how we define the integration. Integration is a summation of the function value multiplied by the small with delta t. So in the limit where delta t tends to 0, this summation will tend to the area bounded below by the curve. Okay, so that is the idea of integration. Now we use this sign, this neck symbol to denote integration. And inside the integration, we have a function to be integrated, right? And that's normally called the integrand. The t is a dummy variable. Now you can use whatever variable you like in the integration. It doesn't matter. You can call it a t, you can call it s. It's a dummy variable. Okay. Now since the integration represents an area, and each of the strip has an area f multiplied by delta t, because f can take on positive value and negative value when f is larger or smaller than 0, right? If f is larger than 0, the area is positive, while if f is more than 0, the resulting area will be negative. So the area does carry sign. Okay, if I integrate this area above the t-axis, I get a positive value. I integrate over the area below the t-axis, I get negative value. And they might get canceled if I integrate from the positive region to the negative region. So there may be cancellation of some of the area. Okay. Now, what is the definite integral? We only state indefinite integral, but what is the definite integral is we have a well-defined beginning and ending point of an integration. So when we integrate from t1 to t2, the lower limit being t1, the upper limit being t2, what we mean is that we are calculating the area, the exact area, bounded below by the graph between t1 and t2. So it represents the orange area as shown in this diagram. Okay. So this is a very precise definition. It is this area, not the area in the other places. So whenever we specify t1 and t2, we know the exact area to be fine. Okay, and if you do the integration for a given function, you should get a number, and the number is exactly that area. Okay. Now the definite integral, as I say, is the area under the curve from t1 to t2. But what is an indefinite integral? Now, indefinite integral, you can think of it in this way. Okay, it is a kind of integration. I integrate a function with respect to a variable, but I know the upper limit. The upper limit is set at t. T is any point you like. Okay, so the integration of f over the ds with an upper limit at t will give you a function of t. Okay, but how is the lower limit? Well, the lower limit I haven't specified, so I don't know where it is. Okay, it may be somewhere here, it may be somewhere there. I don't specify the lower limit. So the indefinite integral in this sense only represent the area up to the curve or under the curve up to a certain variable t, and the lower limit is not specified. And the lower limit not being specified is equivalent to carrying an integration constant. So when you do a indefinite integral, you always result in a function of t, which is the lower limit, which is the upper limit, but you also carries an integration constant. The integration constant is there because you don't know where you start, right? If you start earlier, your area may be bigger. If you start late, closer to t, the area will be smaller, but you don't know where you start. So the c, the undetermined constant, is there to denote, to let you know, remind you that I don't know where I start. Okay, but I know that eventually I integrate up to t. Okay, so that is called the indefinite integral. Now, when I integrate, for example, a function from k to t, suppose the integration of a small f is the big F, right? And so I integrate a small f, I get a big F, and I evaluate at the upper limit t and lower limit k, right? So I get ft minus fk. You may call this fk a integration constant. Okay, so I denote the indefinite integral by the function capital F of t plus an undetermined constant c. Now for the definite integral add up in a certain way. If I, for example, if I integrate the function f from a to b, and then from b to c, now you note that the b is common, okay? The b is the upper limit of the first integral and the lower limit of the second integral, okay? Now you can easily see that these two integrals are represented by these two areas, the pink area and the orange area, right? So if I sum up the two integrals, that obviously result in the area bounded below by the curve between a and c, which is represented by the integral of f from a to c, right? So you can see when the two integrals add up, the b no longer appear. The b seems to be cancelled because just follow the first integral integrate up to b, and then the second integral just follow the integration from b to c. So the b it doesn't matter when the two sum up. It's simply an integral going from a to c. Okay, so that means the area simply add up. And in integration, there's an important theorem, very important theorem we call the fundamental theorem of calculus. Now, the fundamental theorem of calculus is nothing but it states that the integration and the differentiation, they are the reverse operation of each other. So if you differentiate a function A, you get function B, then if you integrate function B, you go back to function A. Okay, and the fundamental theorem of calculus is a more precise way of making this statement. Okay, now you can formulate the fundamental theorem of calculus like this. Suppose you have a function capital F, you differentiate that function, you got the small f of another function. Then that is equivalent to saying that if you integrate the small f, you go back to the big F. Okay, so in this formula, you can see the big F and the small f, they are related by a pair of operation, the differentiation and the integration, but they are opposite to each other. Okay, they are reverse operation of each other. Okay, so from the differentiation, you go from the big F to the small f, and from the integration, you go back from the small f to big F. Okay, now I can also state the fundamental theorem of calculus like this in terms of a single function. If I put this small f, which is the derivative of big F, into the integral, now this is a small f, this is a small f, so I can replace the small f by the big F dt, right? So it becomes something like this. I start with the big F dt, and I integrate it, I get big F. So it's apparently the integration sign seems to cancel the differential sign. Okay, when I differentiate function integrate it, it goes back to itself. I can also state it in another way. Suppose now I don't like the big F. Okay, I don't like the big F, so I write the big F in terms of the integral of the small f, and I put it here. And that will become what? That will become the small f equal to the derivative of the integral of itself. Now again, you can see the operation. The differentiation seems to be canceling the integration. Okay, now these two expressions only state that the integration and the differentiation, the two operations cancel each other, but in different order. Okay. Now let's try to have a proof of the fundamental theorem of calculus. Now we need to be very careful in the proof. We need to understand the integration well in order to do the proof. And the safest way to do so is to start with a definite integral. Because the definite integral, we know what it means. We know the starting point and the ending point. Now we consider the function f as a function of t. We start from a fixed point, which we call t naught, and I integrate from t naught to a certain t. Okay, so that gives you this area. And in the other integral, I integrate from t naught to t plus delta t, where delta t is a sufficiently small interval. Okay, so doing this integral, I calculate the area from t naught up to t plus delta t. Now, if I want to find the difference between the two integrals, right? One from t naught to t plus delta t, one is the area from t naught to t. If I subtract the two integrals, that will give me what? That will give me the area of the yellow strip, right? Because when the two integrals subtract, this area has gone, and I'm left with the area of the vertical strip. And if my delta t is sufficiently small, imagine now my delta t gets smaller and smaller. And in that case, I can replace this area by the area of a rectangular strip, which is the function f, the value of the function f here, multiplied by delta t. Is that right? Now, so if I move the delta t to the left-hand side, if I divide the whole equation by delta t, and I take the limit where delta t tends to 0, the equality will be exact. The two sides will be exactly equal to each other if I'm in the limit where delta t is equal to 0, right? Now, but what is this? If I consider this integral to be a function, okay, I define this integral to be a function, which I may call it a big F. I define it by this expression. When I integrate this small f from t naught to t, I call it a function big F. So this is what? This is a function. Now I look at the upper limit, because the function depends on the upper limit. This is the function variable, right? It depends on the s here is a dummy. Okay. After integration, we will go on, because if I evaluate at the upper limit, lower limit, the s will go on. So the s is not important. You can use whatever variable you would like. But the t here refers to the upper limit. Okay. So here with the upper limit at t plus delta t, this function f is evaluated as t plus delta t. While this function is evaluated at t because the upper limit is t. And this expression is just the difference between the two functions, right? The difference of the function at t plus delta t minus the function at t divided by delta t when delta tends to 0, it is exactly what? It is exactly the definition of the f dt. This is the definition of the derivative of f. But f is this guy. So when you put it back, you arrive at this expression. Okay, but this is exactly what? The fundamental theorem of calculus. If you start with a small f, integrate it, differentiate it, you go back to f itself. Okay. So a summary is that differentiation and integration are the two inverse operations. They cancel each other. Now, but it's important for you to understand that if you start from a small f and you want to find a big F, if you are using an indefinite integral, then you only can find the big F up to a certain constant. You cannot totally determine the big F. You can only know the big F up to a constant. Okay, and that is the so-called integration constant. Okay. Now here are the rules of differentiation. If you start from constant 1, you integrate, you get a t. If you start from a t, you got t squared over 2. For t squared, you got t power 3 over 3. And in general, if you have a t to the power alpha, then the power of the t will be increased by 1. You have t to the raised to the power alpha plus 1. And then you have to divide by alpha plus 1. Okay. And of course, you have the undetermined constant, c, the integration constant. Now, you immediately notice that this formula is not applicable for alpha equal to -1. If you put alpha equal to -1 here, the denominator will be 0. And 1 over the 0 denominator will be infinite, which is undefined. Okay, so this formula is not applicable for the power of t equal to -1. Now, how do we prove it? Whenever we want to prove an integration works like this, we use a differentiation, because the differentiation is the inverse operation of integration. So that means we can check by differentiating this function. If we differentiate this function and we go back to t alpha, that means the solution is correct, the integration is correct. And obviously, when you do the differentiation of this, is go back to t alpha. Now, for sine and cosine, it's rather easy. If you start from a sine, you do an integration, you got a minus cosine. If you have a cosine and you do the integration, you will have a sine. Now, you notice that there's a minus sign here. Okay, if you go from a sine to cosine by integration, you have a minus sign. While if you go from cosine to sine, you don't have a minus sign. Okay, now you can also check by doing a differentiation. The differentiation of a minus cosine is exactly a sine, right? And differentiating sine is cosine. Okay, so that's why this two formula is correct. Okay. So a rule of the thumb is that whenever you are not certain about a certain integration, you just differentiate your result to see if it goes back to the original expression. If it's correct, then if you go back to the original expression, then your integration is correct. Okay, that is a simple way to check your calculation. And for the exponential function, we all know that differentiating exponential function become itself. And so that means integrating exponential function will also become itself. There's no change. Exponential function is not changed by integration or differentiation. Now, we would like to handle the 1 over t. In this discussion, we have warned you that this expression is not applicable for alpha equal to -1, which is t to the power -1. So how do we integrate t to the power -1? Well, it is given by the natural logarithm. The natural logarithm is the logarithm to the base e, where e is the natural number, 2.57 something. Okay. Now we have an example for you. Somebody may ask me, what is then the integration of log t? Do you know how to find the integration of log t? Some of you may have learned integration by parts. You may know how to do it, but let me do it in the reverse way. Suppose I know the answer. The answer is t log t minus t. If you don't believe it, you can simply do a differentiation of this expression. Okay, when you do it, you can see differentiating t is 1. So 1 times log t plus the t is kept unchanged. And I differentiate log t, I get 1 over t. And this 1 over t cancel with the t. Okay, for the last term, I only get 1. Okay, so the last two terms cancel. And eventually I got log t. So that means integrating log t is t log t minus t. But that is not a way of doing mathematics because I already know the answer. I only check the answer. Now, integration is not the same as differentiation. For differentiation, no matter how complicated the function what kind of function you have, no matter how complicated it is, you always can do the differentiation by repeatedly apply the chain rule, the product rule, or the quotient rule, etc. by repeatedly applying this rule, you can do whatever complicated function. You can differentiate whatever complicated function. But integration is not like this. There is no general workable method to integration. And many of, and in fact, most of the function, the integral cannot be expressed in terms of the elementary function. Okay, so there's no guarantee that any of the integration method will work. But normally we will rely on the following method to do integration. The first one is exact differential. The second one is change of variable. And the third one is integration by parts. Now let me discuss about exact differential first. We just rely on the the fundamental theorem of calculus. If I start with a complete differential of a function, integrated, I go back to itself. So basically, if you know, if you can write the function in terms of derivative, then you know the answer beforehand. For example, this function, t cosine t minus sine t over t squared. How to integrate this? But I can check it. I know that the derivative of sine t over t by the quotient rule give me this exactly this expression, right? You can easily check it by using the quotient rule. And so that means I can rewrite this as the complete differential of sine t over t. So the integration cancel the differentiation and I get sine t over t. Okay, but this is not a method of doing, again, not a good method of doing math. It is, I just to say that I know the answer beforehand. Now, how about this? T multiplied by exponential to the power t squared. Now, I noticed that, in fact, this guy can be written as the complete differentiation of half exponential to the power t squared. Why? Because differentiating this will be using a chain rule. The exponential function go back to itself, but then I differentiate the exponent with respect to t, and that gives me 2t, right? So that means t multiplied by et squared is 1/2 of the derivative of et squared, and so that I've got this expression. So integrating it will be canceling the differentiation. So I go back to this function. Okay. The most useful method of integration will be the change of variable. What do we mean by change of variable? Basically, we introduce another function. What is this function is not important. The important thing is that after you introduce this function, you reduce the integral into a simpler form so that you can do the integration with the other variable. That is the idea. Now, suppose t is given as a function of u. So by the rules of differentiation, you have dt equal to dt du multiplied by du, right? So you replace the dt in the integral by a function in terms of u. Okay, now because everything now is given as a function of u now, right? So the t disappear. After this replacement, the dt become dt du, okay? But t is given as a function of u, so the t disappear here, and I multiply by du. Again, the t disappear. And I also can express the t inside the function f as a function of u. So in the whole expression, the t get totally disappear, and I'm left with an integral over u. Okay, and hopefully, if I have a careful choice of this function, I would be able to simplify this integral, and so the integral of u can be evaluated. Okay, let's take a look at this example. I have a function t sine t squared. Okay, now the most typical part here is with the t squared. The sine t, I know how to integrate, right? I know how to integrate sine t, but not sine t squared. That is a problem. So my aim is to get rid of the t squared. And so it is natural to define another variable called u, which is t squared. Because if I put u equal to t squared, the sign, the argument of the sign will become sine u, right? I got rid of the t squared. Okay. If the other variable change in a nice fashion, I would have a chance to evaluate the resulting integral, right? So let's see if it works. If I define u equal to t squared, then t is equal to square root u, right? And the du by this expression is just equal to 2t dt. So I can make dt the subject of the formula. This is du over 2t. I eventually should eliminate this t. So I write the t as square root u. So it becomes 1/2 u to the power minus 1/2 du. That is dt. So I put it back here. This t is u to the power 1/2. Now you can see I'm very fortunate because the u power 1/2 and the u power minus 1/2, they cancel each other. It becomes u to the power 0, which is 1, right? So I'm just left with an integration of sine u, but I know what it is. Integrating sine u is minus cosine u. And eventually I should go back to the original variable. So I change the u back to t squared and I got the integration done. Okay. Now the change of, if you are familiar with doing the change of variable, I think some of the integral, change of variable can be done in your mind without explicitly written out. For example, let me take the same example again. The sine integrating sine t sine t squared. Now in my mind, I can think about this. Instead of making the variable as t, because I now have another t outside, right? I have t dt. But t dt is what? T dt is the derivative of t squared over 2. Is that right? And if I change this t dt to d of 1/2 t squared, then my integration variable will be t squared. And in effect, I have put u as t squared. Is that right? In my mind, I have put t squared equal to u. I just don't explicitly write it right out. Okay, so I just put the t into the dt, and I convert it into d of 1/2 t squared. And of course, I can pick the 1/2 out. And you can see the t squared here match with the t squared in the sign. And so that means I can integrate over. Okay, and I got, in a straightforward manner, I get minus cosine t squared. Okay, so this is a quick way to do it. You just do the substitution. You just do the substitution in your mind. Okay, you don't explicitly write out, but by putting the additional t into the differential, you are doing a change of variable in your mind. Okay. Now another integral that commonly appear in physics looks like this: square root of t squared plus or minus something. Maybe not square root. Maybe it is t squared plus a squared raised to some power. The power may be positive, negative, or fraction. And then you multiply by t, you do the integration. How do you do this kind of integration? Now, a simple way to think about this is, again, use this formula. I notice that dt dt is dt squared over 2. Okay, so I change the integration variable to dt squared instead of t. Okay, so by moving this t into the differential, I change the integration variable to t squared. And I noticed that why I do that, because I noticed that this t squared match with the t squared in the square root, inside the square root. And I can also add a constant a squared in the differential, because the derivative of a constant is 0. So it doesn't change anything. But by doing so, by adding a squared to the variable in the derivative, in the differential, I can match exactly the function in the square root. So in my mind, my u is t squared plus a squared, which match with 1 over square root u. Okay, so I can integrate easily. Okay, because integrating u raised to the power minus 1/2 is u to the power plus 1/2 divided by plus 1/2. And u is t squared plus a squared. So I got the result. Okay, so that's a way to do it. Now here is another example of using substitution, but of using integration by substitution, but I use the trigonometrical function. Now the trigonometrical function is especially useful when we are doing it with this integral. A squared minus t squared square root, or it may morph to the combination to some power. A squared minus t squared to some power. Now, for this kind of integration, we may like to convert the t to another function, which I call a sine u. Now, why I call this sine u? Because I noticed that if I put t as a sine u, this t will become t squared will become a squared sine square u, and after I factor out a factor of a, the guy inside the square root sign will be 1 minus sine square u. And 1 minus sine square u by the trigonometrical identity is cosine square u. And by taking the square root, I only obtain cosine u. And that solves the problem. The problem is that I don't know how to integrate this complicated thing inside the square root sign. But by changing the variable to u with a sine u, I use a trigonometrical formula to simplify the denominator a lot. And in this example, because I know that dt is a cosine u du, a straightforward differentiation of this, I luckily have the cosine u cancel. The denominator and the numerator both contain a cosine u, so they get cancelled. I simply is left with an integral of du, and that's of course u. But I can find the reverse function. T is equal to a sine u, so u is just a sine of t over a. Okay, and don't forget the integration constant. Now, actually, for this transformation, I can for this relationship, I can represent it by using a right angle triangle. If this is a right angle, and this is u, and this is a, the hypotenuse is a, then a sine u is t, which means the opposite side is t. So a, t, and u are given are related this way by this right angle triangle. Okay. Now let's have a break now. But before having a break, let me challenge you with this problem: integrating 1 plus a squared plus t squared. And I give you the hints. The hint is make a substitution of t equal to a tangent u, because I noticed that I have a purpose. I noticed that if I make such a substitution, then the denominator will become a squared multiplied by 1 plus tangent square u, right? But 1 plus tangent square u is secant square u. I don't know if you have learned this formula in your high school. Secant is 1 over cosine, and that means we hopefully can integrate the expression. Now let's take a break for 10 minutes, and during the break, please try to do this integral. We'll come back on 35. If you have any questions, you can come. All right, let's continue. Now, how to do this? I give you a hint that the derivative of tangent is secant square. Okay, Now, actually, this is not difficult to prove. If you don't remember this relationship, you can prove it yourself. You can simply write tangent as sine u over cosine u. So when you apply the product rule, that would be cosine square u in the denominator, and you have cosine u ddu of sine u minus the sine u, the derivative of cosine u. Right? This is a product rule, but differentiating the sine u is a cosine u. So now you have cosine square u. And here, what if you go differentiate cosine u, you get minus sine u. So you have sine square u, right? And you divide by cosine square u. And of course, the numerator is 1. So you have 1 over cosine square u. 1 over cosine square u is secant square u. Okay, that is the definition of secant. Secant is an inverse function, is a reciprocal of cosine. And so, how about 1 plus tangent square u is equal to secant square u? How do you prove it? Well, it's simple. You start with sine square u plus cosine square u equal to 1. Again, if you divide the whole expression by cosine square u, this is what you get, right? You just divide the whole expression by cosine square u. But this is tangent square u. And on the right-hand side is just secant square u. Okay. So we have proved all the formula that you might not know simply by using sine square u plus cosine square u equal to 1. Okay. Sorry, I should write here ds du. So how do you integrate this? Let's make the substitution t equal to a tangent u. So now if you find dt, it should be a secant square u du, right? So that is dt. And here we have a square plus a square tangent square u. And then in the numerator, we have a secant square u du. Is that right? I just substitute the t into here, and I just use this expression for the dt. Okay. Now, but 1 plus t's tangent square, as I say, it is secant square. So the a, one of the a cancel. So I now have this expression. So I have secant square du divided by secant square u. So the secant square got cancelled. And eventually I got u plus c, right? But u is what? U is arctangent t over a. So it's given by arctangent t over a plus c. Okay. So that is the answer. Now define the last method of integration is called integration by parts. How is it doing? Now I put in an extension, meaning that I will not test you in a final exam. That means I will not give you an integral that can only be integrated by integration by parts. Okay, so don't worry about it. The integration by part actually makes use of the product rule of differentiation. Now, if I have the product of two functions, f and g, I take the derivative of it and I integrate it. The integration cancels the differentiation. I go back to the product itself. So I have fg plus c, right? But I can also use the product rule to expand the derivative in the integrand. dfg is df times g plus f times dg. That is the product rule, right? And I integrate it, I got FG. Now, what I'm going to do next, I'm going to move one of the term to the right. For example, if I move FDG to the right, what I get is the following. The FDTG, the integral of it, equal to FG minus dg dt multiplied by F, the integral. Okay. Now, what is the advantage of doing so? Now, for some of the function, you may find that the F dt multiplied by G is difficult to integrate. But if the derivative act on the G instead of the F, in some situation, the integral may be simplified. Okay. For example, especially if G is a polynomial, because when you differentiate a polynomial, the degree of that polynomial will decrease by 1. If you decrease the degree of the polynomial by 1, then it will be easier to integrate. Okay. Now let us take this example. Now this example consists of the sine function multiplied by a simple polynomial, which is just t. Okay. T is the simplest polynomial, right? Now, I want to get rid of this t because I don't know how to integrate t sine t. I only know how to integrate sine t, but not t sine t. So I want to in my mind, I want to get rid of this. So let me imagine this is g. Why I imagine this to be g? Because if on the left hand side I have g equal to t, then on the right hand side I will have dg dt. But dg dt is 1. So after doing the derivative, I get rid of the t. And hopefully I will left with a simple trigonometrical function, which can be integrated easily. So that is the rationale behind my choice of the two functions. Now, so this t, I call it g, and this sine t, I call it df dt, just to fit this form, okay? So on the right-hand side, I have fg. G is t, right? F is the integral of sine t, because the f dt is sine t, so f is the integral of sine t. The integral of sine t is minus cosine t. So fg is minus t cosine t. And then we have, by the formula, minus, then we have f. Again, f is minus cosine t, we know before. dg dt is dt dt, which is 1, okay? So I'm left with an integral of cosine, which is sine. So I complete the integration. Okay. Now, in some situation, you may have to do the integration by parts for more than one times. For example, if this is not t but t squared, then I have dg dt that will reduce the power by 1, but still I have t. So you have to do an integration by part again to get rid of that t. Okay, so this is the way for you to solve some complicated integration. How about this? How to integrate this? Again, I know how to integrate exponential function, but not with the t. So in my mind, I want to get rid of it. Okay, now let me write out the formula and let's do it together. Now the formula is easy to remember. Okay, I have g df dt equal to gf without the integration minus the reverse of these two things, f multiplied by dg dt, the integral. That is the formula. Now in my mind, I have this to be t. Okay, and this is just e to the power minus t. So what is this? This is of course t. F is what? If the f dt is e to the power minus t, then this is what? Integrating of this, right? The integral of this. Integral of this is e to the power minus t, but there's a minus sign go with the t, so the minus sign goes out. I have this function. Okay. F is again this one, right? And dg dt is dt dt, right? Which is 1. So I put all the things back to this equation. And I will have this guy integrate over be equal to minus te minus t. Sorry. The minus sign here cancel with this minus sign, so I have a plus sign here. Well, this goes as e to the power minus t. This is 1. Okay, I just multiply by 1 here. So the last line will then be integrating the e to the power minus t, which is what? Which is minus t e to the power minus t plus the constant c. Okay, so I complete the integration. Okay. Now, not every integral can be expressed in terms of elementary function. Now, doing integration is sometimes useful in physics, but that is not very important. Don't worry if you can't do a particular integral. Be familiar with the common integral. If the integral turns out to be particularly difficult and you don't know how to do it, don't worry. That's my advice to you. If you cannot do an integral, then you may find in integration table in the old days. In the old days, there's in the library, there's a big book containing all known integration, and that's called integration table. Nowadays, we no longer rely on the integration table because we have the internet, and we have a software like Mathematica or MATLAB that allows you to find the integration. And even nowadays, some sophisticated calculator, electronic calculator, they may have a function for you to find the integral. Or you can do it in online calculator. The Wolfram Alpha is a famous website containing a calculator which can help you evaluate the expression, different kind of computation symbolically. So there's a symbolic calculator, okay? Or if you simply want a numerical result, you can use a numerical method. You just sum up the vertical strip, effectively using a computer to find a numerical answer to that differential integration. If you only want a numerical result, okay. And these are the basic idea of integrations you may review in the e-learning module, okay. Now these are the extension module. You may not want to know more on the general formula sum of the numerical methods. If you like to learn the numerical methods for using integration, for doing integration, you may take a look at this. And there are also more difficult integrals outlined in this section of methods of integration. Okay, so we stop here for this part. So let's continue with chapter 3. Okay, we have a long way going sidetracking to integration. We are now back for solving the problem, the kinematic problem. Now let's talk about the simplest problem. The simplest problem is what you learn in high school, the uniform accelerated motion. Uniform accelerated motion. I know you have learned how to derive the equation of uniform accelerated motion using a graphical method. But here, I want to do the same thing, but using integration. Okay, so how do we do it? Now, a uniform acceleration means the acceleration is a constant. So A is simply a number. For example, the acceleration due to gravity is 9.81 meters per second squared, which is a constant. Okay, so our equation of motion, it will be just dv dt equal to A, which is a constant. Now, so we can integrate both sides of this equation. Okay, And you can also use the derivative. You can also treat the derivative symbol as fraction of dv and dt. And so you move the dt to the right-hand side and you integrate both sides. Okay. So I integrate the left and the right side, and this is the equality. Now, integrating v, dv is of course v, right? But how about integrating a? A is a constant, is a given constant. It is not a function of time. So that means I can take it out of the integral, and the integration simply give me a t. And don't forget about the integration constant. Now, for this step, I must warn you. This operation works, integrating a dt equal to at. It works only when a is a constant. If a is given as a function of time, you cannot do it. You have to do an integration. Okay. Sometimes a is given, as I said before, a is given as a function of velocity and position. But the velocity and the position are unknown function of time. So you cannot simply write integral a dt as at, because a contains an implicit function of time through the position and the velocity. Do you understand that? Because you have a as a function of, it properly contain t, but you may contain x, and you may contain v. And both x and t are unknown function of time. You do not know this function, right? So there's no way for you to integrate it over time. You do not know it. You don't know how to do it, because these two functions are unknown. The two functions exactly what you want to find. So this step works only for a equal to a constant. Okay. So let's continue. Then we have this expression. How to fix this constant? How to fix the constant? How to fix the constant c? Well, we have the initial condition. The initial condition is important now. We know that at time 0, when the motion starts, the velocity v is equal to the initial velocity, right? Now, what I mean by v here is the velocity at the general time t. Okay, so I consider v here as a function of time. But when the time is 0, I know the initial velocity. The motion starts with a velocity u, and that particular time v is to take on a particular value, and that value is given. That is u. So if I put t equal to 0 in this equation, I get v equal to u, but on the right hand side is equal to c. And that means c is equal to u. And so I know u, I know c now. C is just equal to u. So the equation reads v equal to u plus at. But this is what? Oh, this is the simplest equation for uniform accelerated motion. The final speed equal to initial speed plus the acceleration multiplied by time. V equal to u plus at. That is the first formula you learn when you learn about the uniform accelerated motion, right? Now we have not done yet because we eventually want to find x, but we know that x is dx dt, but v is dx dt, right? That is a definition of the velocity. It is a derivative of x with respect to time. And now I know v is u plus at. So I can integrate both sides with respect to t again. Now notice that now u is a constant, a is a constant, right? So the right-hand side is a known function in time. So you can integrate over time. You know how to do it. So if I integrate both sides, the left-hand side gives me x, the right-hand side gives me ut. Integrating t will be t squared over 2. That means I got half at squared. And don't forget, when I do an integration, an indefinite integral, I always have to remember I have an integration constant. Now I call this another integration constant c prime. Now, the initial conditions are there because we rely on the initial rely on the integration constant to insert the initial condition. Okay, so the initial condition are inserted through this integration constant. So don't forget the integration constant. Otherwise, there's no way for you to specify the initial information of the motion. Okay. Now, what is C prime? If we consider the particle to start moving from origin, at origin x is 0. So at time 0, t is x is 0. If I substitute this two condition into this expression, x is 0, t when t is 0, so both of this term is 0, and that means C prime is 0. And so I have x equal to ut plus half at squared. That is the second equation you learn for uniform accelerated motion. How about the third one? Well, I can use this expression. I can use v equal to u plus at to eliminate the t. Okay, I make t the subject of the formula, t equal to v minus u over a, and then I substitute this t into this equation. Okay, now so I factorize this equation first, and I substitute t as v minus u over a. Okay, so the a here in the bracket got cancelled. And after some algebra, what I get is 1 over 2a v squared minus u squared. And when I move the 2a to the left-hand side, it will become v squared minus u squared equal to 2ax. And that is, of course, the formula I learned in high school also. So I got the three formula I learned in high school. But now we derive it by using integration. Now remember, when we study motion at the beginning, we start with a description of motion by specifying x as a function of time. Okay, and as we say, the velocity is the derivative of x with respect to time, and that is represented graphically by the slope of the tangent to the xt graph. So the slope of the tangent to the xt graph will give you the velocity. And if you plot the slope at different points, you will end up with a graph of the velocity versus time. So a first differentiation allows you to go from the displacement to the velocity. And again, if you do the same thing, if you measure the slope of the tangent everywhere on the curve, and you will find the acceleration. The acceleration is the derivative of the velocity and the slope of the VT curve, of the tangent to the VT curve. And that gives you a graph of the acceleration versus time. In our example, we have the displacement, the position x given as a quadratic function in time. So after a differentiation, we have a uniform, you have a straight line. So the velocity is changing linearly with time with a constant acceleration. So we differentiate once more, we have a horizontal line, which means the acceleration is a constant. Now, when we go back, we start with a constant acceleration. And when we do the integration of a, the acceleration, we are finding the area below the curve, right? This is an AT graph. We do an integration of a over time. We have the velocity, and that is represented by the area bounded below by the AT graph. And that gives you, at every point, that gives you the velocity time graph. If we integrate the velocity again, we will get the x, the position. Okay, and the position is just given by the area below the VT graph. Okay. Now I show this graph for you. The shape of the graph that I showed to you is for constant acceleration only. But the relationship between the xt, vt, and at graph, they are in general. You go from x to v and then to a. Each time you have a differentiation. If you go from a to v to x in this direction, then every time that involved will be an integration. Okay. If you go from x to v to a, to V to A, then you are looking at the slope of the graph. If you are going from A to V to T, then you are good looking at the area bounded below by the curve. Okay. Now let's extend our discussion to 2 dimensions. For projectile motion, we have the acceleration due to gravity in the downward direction. And the acceleration vector is given by minus gj, where g takes on the value of 9.81 meters per second squared, right? Now, so I can decompose the equation of motion into 2 parts, the horizontal motion and the vertical motion. For the horizontal motion, the x component of the velocity does not change with time, because the x component of the velocity, it does not subject to any acceleration. So dvx dt, which is the acceleration, is 0. Okay, so that means no acceleration in x direction. But for the y direction, the y component of the velocity is subject to a downward acceleration, a downward constant acceleration of minus g. Okay, so now we have 2 equations, one describing the horizontal direction, the other describe the vertical direction motion. Okay, and what are the initial conditions? Initially, at time 0, the initial velocity x component of velocity is ux. The initial y component of velocity is uy. And if you like, you can write the ux and uy in terms of the speed, the initial speed, and the angle. Horizontal ux is u cosine theta, with the vertical component uy is u sine theta. Okay. But how about these 2 equations? We have solved it before, right? dv dt equal to a constant, right? We solved it before, right? Where? We solve it here. dv dt equal to a constant. Is that right? We have solved this equation. The only difference is what? The only difference is now we are dealing with the y component. And the a, then the a is what? Is minus g. So we simply can replace the a with the minus g to get the answer. Okay. So we just copy this formula. Of course, this is y now because we are dealing with the vertical direction. This is uy, right? We replace a with minus g and we got the answer. So that means I can simply, for the y direction, I can simply replace everything with an a by minus g. And I got the y direction motion. The x direction motion is much easier because now I don't have an acceleration. And so the velocity doesn't change. And the position will just be equal to the initial velocity, horizontal component velocity multiplied by the time. So I've solved the whole motion. Okay. Now you can always put a equal to 0 in the uniform acceleration equation of motion to find the x component of motion. And for the y component of motion, you simply put a equal to minus g. Okay. So you can see solving a 2-dimensional problem. For solving a 2-dimensional problem, we can actually decompose the problem into 2 1-dimensional problems. And for each of the problem, we know the solution. So after we combine the 2 solutions together, we solve the 2D problem. Okay. I don't repeat here. I just this I've shown to you in the last lecture about 2D motion. I just grouped the velocity together, the 2 components of velocity together. So it becomes uxi plus uyj is u vector. And also uxti plus uyt, uytj is u vector t. Okay, so this is just a vector way of writing the velocity and the position of the particle. Okay. Now let's do something a little bit more complicated. Let's do it time-dependent acceleration. Now, For the time-dependent acceleration, what I mean is that the force is given as an explicit function of time. It is not given as a function of position or velocity. It is given to you as a function of time. Suppose we have a variable force. Suppose now I'm pushing you periodically, and I can describe this force as a function of time. Okay, so the force is known. It's a known function of time. I know how it varies with time. Okay, so the acceleration will be just given by the force divided by the mass m. That is Newton's second law. And the differential equation of motion is dv dt as a function of equal to a, which is a known function. But since a is given a function of t, I can integrate both sides because I know a, right? So I can integrate a to have to give me v, right? And v is dx dt. So I can integrate this equation once more to get x. Okay, so it's quite straightforward to find v and then find x. We simply go through two integration, direct integration over time. Okay. Now let's have a simple example. Suppose the acceleration is linearly increasing with t. It goes at beta t, where beta is a constant. Initially, the velocity is 0. Initially, the position is at the particle is at the origin. Okay. So the first equation is a equal to dv dt, but a is beta t. We integrate both sides. So we got v as integrating beta t dt, and that's a constant of integration. And so what I got is half beta t squared plus c. Okay. Now we know that initially the velocity is 0. So that means when t is 0, v is 0. So that means c is 0. Okay. And so we find that v is half beta t squared, but v is dx dt. We integrate this equation once more to find x. And so we are integrating t squared, and that gives me t cubed over 3. When combined with this 1/2, I got 1/6 beta t cubed. And don't forget, I have a integration constant. I call it c prime. And because my motion starts at the origin, at time 0, the x is 0. And so c prime is also 0. And so eventually I got x equal to 1/6 of beta t cubed. Okay. Now let's do something slightly more complicated now. That is a real challenge. Okay. We now assume the force is dependent on x and v. Okay. But not explicit function of time. X and v, they are unknown function of time. Okay. And so Newton's second law tells me that my net force divided by m, I got the acceleration. So the acceleration is given as a function of xv. Now, note the difference. The acceleration is a known function. I know how the a depends on x and v. What I don't know is how x and v depend on t. That is the unknown. Okay, so although I know the functional form of a, but I don't know the functional dependence of x and v with t. So that makes the problem difficult. Okay, if you like, you can write x as x and v as dx dt, and that result in a differential equation. I can write dv dt as d squared x dt squared. And here I have a differential equation, a second order differential equation in x. Okay. So in this situation, straightforward integration is not possible. And solution in the closed form is possible only for the simplest case. And for complicated situation, we have to rely on computer. Okay, we have to do it numerically. We cannot simply do it with a pen and a paper. Now let us discuss a simple example, a motion in a viscous medium with no gravity. Suppose I have a ball of mass m, and it is projected with the initial speed v0 into a viscous medium. A viscous medium may be water, maybe some honey, which is very viscous. And you can imagine that if I project a ball into that medium, that would be a resistant force. And I assume that the viscous force is given by minus kV. Okay. Now, how to interpret this? I assume that the resistance or the viscous force is proportional to the velocity. That means if I move faster, I will be subjected to a larger resistive force. Okay. The resistive force get larger when I'm moving faster. That is what this equation means. And the K is simply a proportional constant. It depends on a complicated factor, how viscous the medium is, and how large is your object, etc. Or the shape of the object. We all put all those complicated factors in the K, the constant. The minus sign is there, meaning that the force is now opposite to the velocity. So if I'm moving in this direction, the force will be resisting me my motion, so it goes in opposite direction, resisting my motion. By Newton's second law, I know that the A is F over V. And from this equation, I have minus KL over MV. For shorthand, I define B as K over M, just to write less. So acceleration is given by minus BV. So the equation of motion will be dV dt equal to minus BV, right? A is dV dt. So I now have set up the equation of motion. Now it is a simple first order differential equation. It is first order because it involves only the first derivative of V. And it is very simple because it only contains V on the right-hand side, and not a complicated function of V. Now you can solve this differential equation. Let's look at what this equation means before solving it. This equation means we have to find a V as a solution, such that that function of time, when I differentiate that function, it will go back to itself. The only thing that it come out will be additional factor of minus B. That means I want to find a function such that when I differentiate it, it will give me the function itself and with a extra factor of minus B. So that's what we want. We want to find such a function with this property. Okay. Now, what kind of function will have this property? My guess will be this function, the exponential function. When I differentiate exponential function, it goes back to itself, right? So when I differentiate the V, it goes back to V. And how about the minus B? How can I come up with a minus B in front? Well, you see in this expression, I assume that in exponential function, it's not exponential simply t, but exponential beta t. So upon doing a differentiation by the chain rule, I will get a constant beta O, and that constant may match with this minus B. Okay, so in defining this trial solution, I suppose I have an unknown parameter beta, and to make things general, I also will have another constant A that goes before the exponential function. So I have two unknown parameters. So let's see how I fix them. Okay. Now, in order for this to be a solution, it must be satisfying the equation. So I give it a try. I try to prove it. If I substitute this solution to the left-hand side of the equation, I differentiate it. What I got is beta A exponential beta t. The beta factor come out upon differentiation by the chain rule, right? The right-hand side is simply minus BV. So I just copy the V here without doing anything. Now, in order to make the left-hand side to be equal to the right-hand side for all time t, I have a certain condition. Now, I noticed that the exponential factor that contains the t will cancel on both sides. The A will also cancel. And that leaves me with beta equal to minus B. Now, how do we interpret that? All the t factor cancel on both sides means that the equation could be satisfied for all time, because this equality does not depend on time. And that means the equation, the left-hand side and the right-hand side can be made equal for whatever time we like, okay? But there is a condition. The condition is that the two constants, the beta and b, must be related to each other by beta equal to minus b. I must choose beta equal to minus p to satisfy the equation. And so what is the solution? The solution will be just this, but just beta replaced by minus b. So the solution is a exponential minus bt. And then how do I fix the constant a? Well, the constant a is the integration constant, in fact, and I fix it by imposing the initial condition. At time 0, my ball is just projected into the medium, so it has an initial velocity v0. And that means if I put time equal to 0, v is equal to v0. But when I put time 0 on the right-hand side, the exponential factor is just 1, and I will get an a. So a is just v0. Okay, so now I fix all the constant, and I got a solution as v equal to v0 exponential minus bt. That is my solution to the problem. Now, you look at this solution, you see it makes sense. Because an exponential function with a minus sign in this argument means that the exponential function is decreasing with time, is decaying, okay? And its initial value is v0. If I put t equal to 0, v is v0. And when time proceeds, when time getting large, this exponential factor e minus bt will be decreasing exponentially like this, okay? So that match our physical assumption, because when I project a ball into a viscous medium, its speed will be decreasing with time, right? Because of the resistive force. The resistive force decreases the speed of the object. So the speed will decrease with time, and the decay here is exponential function. Now, we also know that the argument, the factor that inside the exponential function must be a dimensionless. If you don't believe it, you consider what? You consider the Taylor series. The Taylor series of exponential function goes like this, right? If you have e to the power cos c, the first term will be 1 plus cos c over 1 factorial plus cos c squared over 2 factorial. This is square, sorry. Plus cos c cubed over 3 factorial, etc. How can you have a cos c added to 1? How can you have a cos c squared added to 2? Added to 1? How can they add it together? The only possibility is that this cos c is dimensionless. If it's carry a dimension, cos c cannot be added to 1 because they are of different dimension. So that means for physical expression, the exponential function may take on an argument that is dimensionless. And so for this situation, bt is dimensionless. And that means b has the inverse dimension of time. And I can define 1 over b at the time, which is called damping time scale. It carries a dimension of time. So I define tau as 1 over b, and I rewrite the b as k over m. So it becomes, the tau becomes m over k. Okay. Now, what is the meaning of tau? Now, in terms of the tau, I can write the solution as e to the power minus t over tau. What does it mean? Tau is a time. And when t is equal to this time, tau, the exponential factor is simply e to the power minus 1, right? Because here we have t over tau. So if t equal to tau, this is just 1. So I have e to the power minus 1, which is 0.368. It is about 37% of the original value. So that means what? That means when my time is equal to tau, the velocity has decreased to about 37% of its initial value. if the initial value is v naught at time tau, at this particular time tau, the new speed will be about 0.37 of v naught. Okay, so that characterizes the time for the velocity to decrease substantially, because 37% of the initial value means a decrease by a substantial amount. So we can use this time to characterize how fast the system decay with time. Okay. And I can check that the tau actually has a correct dimension of time. How do we check it? We go back to this equation. For this equation, the dimension of A is LT minus 2, the dimension of acceleration. The dimension of V is LT minus 1 meter per second. So the dimension of B is the dimension of A divided by the dimension of V. If I divide this two dimensions, I got a dimension of the inverse of T. So that means 1 over B has a dimension of time, which are defined as tau. Okay, so that is the idea. So that means the tau has a dimension of time. That is a time. Now, another thing to note that is the beta and A have a different nature. We have introduced two constants in assuming a solution. We have assumed a solution to be in this form, which contain two constants, A and beta. Now, but they are of different nature. The first constant beta is eventually shown to be minus B, which is determined by the parameter of the equation. And that means in order for the solution to work, you have to choose beta equal to minus B. You don't have other choice. That already determined by the equation itself, determined by the motion. But for the other constant A, you can see it is equal to the initial velocity. So it depends on how fast you project the ball initially into the medium. It does not depend on the equation of motion. It depends on initially with what velocity you project it into the medium. So they are of different nature. Okay, now let's stop here at this moment. And